Hello and welcome everyone. Today we are solving the question invert binary tree and let's get started. So this question is about the tree data structure and the algorithms that we can use. So looking at the problem, we see that given the root of a binary tree, inverts a tree and return its root. So what we are referring as a root here is the first node in the tree. And they actually show how the inversion happens. So if we'll look into the given example, we have the initial tree that looks like this, and we are changing um, the left subtree, all the nodes in the left subtree with all the nodes in the right subtree. So basically, as we go down through the tree, we can see that all the nodes that were in the uh, left subtree are now on the right subtree. So the 7 was on the right, but in the result, it turned out to be on the left. And this is true for all the levels. We can see that mm, this is the case since we are changing 3 with 1 in the left subtree of this particular um, subtree. So and the interesting question would be, how do we invert a tree that's empty? In that case, we just return an empty. Uh, yeah, we just return. So in the understanding phase, we see that it's a tree data structure, and in the second stage, we want to match this current data structure with the algorithm that we can use. So most often we can use depth first search or breadth first search algorithm and traverse through the tree recursively uh, and solve this particular question. So I'm thinking of using a depth first search in this question. So the way we're gonna work with this problem, I want to go as deep as I can through the levels and say uh, when I'm left with only, um, say, uh, yeah, when I'm left only with left subtree and the right subtree, I want to swap it. But one question that I would ask the interviewer is that is the binary tree complete, or can there be a case when, say, in both of the cases we see that the binary tree is actually complete. Uh, but most often than not, it might not be the case because, say, we have a empty node on the right and we have an actual node with a value on the left. So we want do we have such a case? And I assume we have. So the number of nodes in trees in range 0 to 100. Okay, so we are not given any information about the binary tree being complete. So I think we need to assume that uh, the tree might have an empty node in its subtree. So in this case, how we are going to implement it, right? So first things first, let's define our DFS function, where we will be passing our root. And in this DFS function, I want to return none if there's no root, because as we can see from this example, if there's no root, right, if not root, um, I just want to return none. So this is our one of our base cases. In the case when we just don't have a node, we just want to return none. Say we traverse through and I want to go through this tree bottom up. So I want to go as deep as I can first and then work my way up to the root. So in this scenario, once this is going to trigger, if we look into this particular example, it's going to be triggered when we reach down to the node with a value of 1, and and try to go deeper to the left, but we cannot, so we just return back none. So we have returned none, and then we start, and I want to like sort of save it there, right? So I want to save it. Otherwise, I want to save the say, and I also want to make sure that there is actually. Um, yeah, I think I don't have to do that, but let me see. The left is gonna be equal to root dot left, and right is going to be equal to root dot right. All right. So what are we doing here? Um, we are trying to get the left subtree and right subtree. So from here, we are returning. Say when we return none, we will end up in this particular node. And what I want to do is say um the left. I want to assign root dot left to root dot right, and root dot right is equal to, I think I can just do this some Python here. Root dot right, right, and root dot left. Root dot left is going to be equal to root dot right, and root dot right will be assigned to root dot left. So from this, we had none in both of the cases, so we just swap them together, and we just want to return the root. All right, return the root. So when we return the root, we return back up 1, right? So from this, when we return back up 1, um, our parent element is going to be 2, and our right node is going to be 3. So we swap them together and then return back 2. So however, one thing, let's try it with an edge case when we don't have a node, right? Say the tree just looks, say we don't have a node with a value of 3. So from this, we say root dot left, which is going to be 1, and the root dot right, which is going to be 3, and I want to swap them together. So I'm going to have none value to my left and all the values from the left subtree on my right. And then I return back up 2. So I think this looks good to me. So let me return from this algorithm, let me return DFS passing in the root that I'm given. And let's evaluate this algorithm. So since we are traversing through all the nodes in the tree, it's going to be big of n time complexity, and uh, yeah, and the space complexity would also be. Um, I think space complexity is kind of tricky because it will, oh yeah, it will be the height of the tree. So in the work, like, since we are going all the way down, I think it's gonna be a big of age where the age is the height of the given tree. So let me try running this. Uh, all right. So looking into this particular case, we have 472, and then 6, 9, 1, and 3, and I think we just missed to the left or the right or the right. Um, I think we don't need these. Yeah, we don't need that. Um, mm, it just says 6, 1. So if there's no root, we just return back. Otherwise, we take. Oh, I think there's one trick. So we wanna call our DFS to. Yeah, we are not calling our DFS function. Yeah, I understand this case. So, uh, think, yeah, I think we had. Yeah, I think uh, there should be something like DFS passing in root dot left, DFS passing in root dot right. Yeah, I think we just like we were doing it from like as we go down, but I want to do it bottom up. So yeah, and then I think I can just say this should be equal to right and left. Right. Yeah. So let's see. Yeah, this question was a good one, I guess. So I'll see you in the next one.